Example 1. Suppose we know that the sum of the first n terms of the series, the sum from n equals 1 to infinity of a sub n, is s sub n equals a sub 1 plus a sub 2 plus all the way through to a sub n equals 2n over 3n plus 5. Then the sum of the series is the limit of the sequence, open bracket, s sub n, close bracket. The sum from n equals 1 to infinity of a sub n equals the limit as n approaches infinity of s sub n equals the limit as n approaches infinity of 2n over 3n plus 5 equals the limit as n approaches infinity of 2 over 3 plus 5 over n equals 2/3. In example 1, we are given an expression for the sum of the first n terms, but it's usually not easy to find such an expression. In example 2, however, we look at a famous series for which we can find an explicit formula for s sub n. Example 2. An important example of an infinite series is the geometric series. A plus AR plus AR squared plus AR cubed all the way through to A times R to the power n minus 1 plus ellipsis equals the sum from n equals 1 to infinity of A times R to the power n minus 1, or A does not equal to 0. Each term is obtained from the preceding one by multiplying it by the common ratio R. We have already considered the special case where A equals 1/2 and R equals 1/2 on page 708. If R equals 1, then S sub n equals A plus ellipsis plus A equals n A approaches positive or negative infinity, since the limit as n approaches infinity of S sub n does not exist if the geometric series diverges in this case. Look at the sidebar. Figure 1 provides a geometric demonstration of the result in example 2. If the triangles are constructed as shown and S is the sum of the series, then by similar triangles S over A equals A over A minus AR. So S equals A over 1 minus R. See figure 1. Back to the text. If R equals 1, then S sub n equals A plus ellipsis. And I read this sentence already. A equals and A approaches positive or negative infinity. Since the limit as n approaches infinity, S sub n does not exist if the geometric series diverges in this case. If R does not equal to 1, we have S sub n equals A plus AR squared plus ellipsis all the way through to AR to the power n minus 1. And RS sub n equals AR plus AR squared plus ellipsis through AR to the power n minus 1 plus AR to the power n. Subtracting these equations, we get S sub n is less than R S sub n equals A minus A R to the power n. I guess this is definition 3. S sub n equals A open 1 minus R to the power n close over 1 minus R. If R is greater than negative 1 and less than 1, we know from section 11.1.9 that R to the power n approaches 0 as n approaches infinity. So the limit as n approaches infinity of S sub n equals the limit as n approaches infinity of A open 1 minus R to the power n close over 1 minus R equals A over 1 minus R minus A over 1 minus R. The limit as n approaches infinity of R to the power n equals A over 1 minus R. Thus, when the absolute value of R is less than 1, the geometric series is convergent and its sum is A over open 1 minus R close. If R is less than or equal to negative 1, or R is greater than 1, the sequence open bracket R to the power n close bracket is divergent by 11.1.9. And so by equation 3, the limit as n approaches infinity of S sub n does not exist. Therefore, the geometric series diverges in those cases. We summarize the results of example 2 as follows. The geometric series, the sum from n equals 1 to infinity of A R to the power n minus 1 equals A plus AR squared plus ellipsis is convergent if the absolute value of R is less than 1 and its sum is the sum from n equals 1 to infinity of A R to the power n minus 1 equals A over 1 minus R, where the absolute value of R is less than 1. If the absolute value of R is greater than or equal to 1, the geometric series is divergent. Sidebar: in words, the sum of a convergent geometric series is first term over 1 minus common ratio.